Our next type of discontinuity is called a jump discontinuity. Jump discontinuities are going to happen whenever you have some sort of discrepancy in the one-sided limits of a function. So a jump discontinuity, let's assume that the limit as x approaches c from below of a given function exists. The limit as x approaches c from above of f of x exists. And it is important for a jump discontinuity that this be a true statement, that the one-sided limits exist. However, if we have the situation where the limit as x approaches c from below does not equal the limit as x approaches c from above of a given function, then we have a jump discontinuity. And graphically what's happening here, you'll see why this is called a jump. I'll let this be my value c. If the graph is approaching a value, and that's a graphical representation right there, that the limit as x approaches c from below exists, approaching some value from the left. And if I'm approaching some value from the right, but not necessarily the same place, so now I've met these criteria. The one-sided limits both exist, however they are not equal to each other, and I get this jump discontinuity. And you can see why it's called that, because the graph literally jumps to another place before it resumes. We should also make a note here, very similar to when we talked about removable discontinuities, that f of c does not have to be defined for a jump discontinuity to exist. In other words, I could have said f of c, I could have let it be this value from below, I could have let it be this value from above. I also could have just let it be any value I wanted. This discontinuity does not hinge on what f of c is doing. So a function where we can say that there's a jump discontinuity, and a function we looked at earlier in Unit 1, if we consider the function f of x equal to the absolute value of x divided by x, we can say right off the bat that f of 0 is undefined. And in fact, that will tell us there's a discontinuity. The question is what type? Well, we looked at this graph earlier, and what we said was the limit as x approaches 0 from below of f of x is equal to -1. For all negative values of x, the absolute value forces them positive in the numerator, and then they get divided by their negative selves in the denominator. So this is actually a constant function to the left of 0, holding it -1. And the limit as x approaches 0 from above of this given function. So now we're talking about positive values. It ends up being divided by itself, and as we saw, that was equal to +1 coming at it from the right side. So my one-sided limits don't match, and so since the limit as x approaches 0 from below of f of x does not equal the limit as x approaches 0 from above of my function f of x, then we can say f of x has a jump discontinuity at x equals 0. So very important for a jump discontinuity. The one-sided limits did have to exist, but they weren't equal to each other, and that's what gave us that jump in our graph, and that's our second type of discontinuity.